And finally, the last alkene reaction that we're going to cover is another one that proceeds with syn addition, and this is called hydroboration-oxidation. So hydroboration-oxidation is yet another method to convert alkenes to alcohols. So we are adding the equivalent of water across the double bond, but we're not actually using water as a reagent. So the process of hydroboration oxidation occurs in two steps. The first step is hydroboration, and that can be carried out using BH3, which is complex to tetrahydrofuran. This is an ether solvent. Or diborane, B2H6. There are some other boron reagents that can also be used. This is just a couple of examples. And then the oxidation step is carried out using hydrogen peroxide and base. So if we start out with ethylene and we carry out hydroboration oxidation, we can make ethanol. If we start out with 1-butene, unlike what we saw with our other methods to make alcohols, in this case, we make 1-butanol, not 2-butanol. So what we have here is called non-Markovnikov addition. Non-Markovnikov addition of H and OH. In this third example, we have issues of regiochemistry as well as stereochemistry because we have a ring. So we will get non-Markovnikov addition, but what's observed experimentally is that we also get syn addition. So both the H and the OH are going to add to the same face of the ring so that our hydrogen adds here and our OH adds here. And we will get addition to the other face so that our hydrogen is in front and our OH is also in front. Hydroboration oxidation gives us non-Markovnikov and syn addition of H and OH. So this method is complementary to acid catalyzed hydration or oxymercuration demercuration because it gives us the opposite regiochemistry. So the overall reaction, we have our 1-methylcyclohexene if it's treated with BH3 and THF, followed by hydrogen peroxide and hydroxide. We are going to get a mixture of enantiomers resulting from non-Markovnikov syn addition of H and OH. So in part 1, the hydroboration step, it's actually 3 equivalents of alkene react with 1 equivalent of BH3 to give an organoborane, or more specifically, a trialkyl borane. So that means that we're adding hydrogen and the boron across the double bond. And then we get this intermediate. In part 2, the oxidation, we treat the trialkyl borane with hydrogen peroxide and hydroxide, and now the boron is replaced by a hydrogen. And so the end product is our alcohol. Now, you're not going to be responsible for the mechanism, but I do want you to know a few of the mechanistic details that are responsible for the observed regiochemistry and stereochemistry. So what's going on in the hydroboration? So starting out, we have our alkene, and then the borane is going to approach. Now, it can approach different ways, where the boron is close to the alkene carbon that is more substituted, and the hydrogen is close to the alkene carbon that's less substituted, or the other way around. Now, this starts out, it's called a pi complex, where the pi electrons are sharing electron density with the boron. From this pi complex, we get to this square transition state. The boron, because it is receiving electron density, the boron takes on a partial negative charge, and the carbon diagonally across from it has a partial positive charge. Down here, the boron has a partial negative, and then the carbon diagonally across has a partial positive charge. Which one of these is going to be better? One way we can think about it is based on sterics. So here we have a couple of hydrogens that are bumping into this methyl group. whereas here our hydrogens are only bumping into another hydrogen. That's not such a big deal when we first have hydrogens. But remember, one of these reacts with three of these. So on the first step, we're going to have hydrogens here, but on the second step, we're going to have one hydrogen and one alkyl group, and on the third step, we're going to have two alkyl groups. And so sterics become very, very important. So the preference will be to line up where the boron is closer to the less substituted carbon so that there's less steric hindrance. Another way to think about it is based on this partial positive charge. Here we have a partial positive on a carbon that is connected to a couple other carbons and a hydrogen. Here we have our partial positive on a carbon that's connected to three carbons. And so just as a tertiary carbocation is more stable than a secondary carbocation, a tertiary carbon with partial positive charge will be more stable than the analogous secondary carbon. So this carbon can better bear the partial positive charge. So between this transition state and this transition state, this is the one that is preferred. So from here, we end up with our hydrogen and BH2. So this is what we get after the first step. Now this is going to repeat where this lines up with a second molecule, and this is where the regiochemistry becomes even more important. And now we have a dialkyl borane, and then this gets repeated a third time where this approaches a third molecule of the alkene, and we get our trialkyl borane. So I want you to remember this transition state because this is what's responsible for the observed regiochemistry as well as the observed stereochemistry. Notice in this case we have the hydrogen and the boron adding to the same face. Well, do we really care about the hydrogen and the boron adding to the same face? What we're interested in is the final product, our alcohol. So where's the hydrogen relative to the oxygen? So the second step oxidation, the base is going to grab off a proton from hydrogen peroxide, giving us the peroxyanion. And then this is going to add to the boron, and we get some rearrangement around here so that this oxygen becomes connected to this carbon from the same face. So now we have this oxygen connected on the same face as the hydrogen that was added in the first stage. This is going to happen 3 times so that our trialkyl borane is converted to this trialkoxyborane. And then water is going to break this up, leading to our final product where we have the hydrogen and the OH have added to the same face of the alkene. So non-Markovnikov syn addition. So now that we've looked at just a handful of reactions of alkenes, we have looked at several reactions that can convert an alkene to an alcohol. So let's compare those reactions. If we are starting out with 1-butene, if we were to carry out our first method, which is acid-catalyzed hydration, so we're adding H3O+. This might be water with sulfuric acid, or it might be written as dilute sulfuric acid, but this is what we're adding. And keep in mind, this gives us Markovnikov addition because of the mechanism. So the alkene is going to share electrons with the H+, leading to the secondary carbocation in preference to the primary carbocation. And so the hydrogen adds to this carbon, with the secondary carbocation is the intermediate, and then water adds to that carbocation, and then there's another proton transfer step leading to this alcohol. Our second method was oxymercuration demercuration. So this is where we're using mercury acetate followed by sodium borohydride, mercury acetate in water and THF followed by sodium borohydride. And this also gives us Markovnikov addition. Now our third approach is to use hydroboration-oxidation, so we can use BH3THF, followed by hydrogen peroxide and hydroxide. And here we get the opposite regiochemistry. We get 1-butanol instead of 2-butanol. If we look at a second example, if we treat this with H3O+, well, again, we can make this, but there's more to it than that, and we need to think about the mechanism. Once again, the alkene will share its electrons, grab a proton off of H3O+, and then the resulting intermediate, the carbocation, is going to look like this. This is a secondary carbocation because this carbon is connected to 2 carbons, and it could happen that we could get a carbocation rearrangement where this methyl group could take its electrons and share them over here, which would give us this carbocation, which is now tertiary, and then water can add, proton transfer, and we end up with this product. So we get Markovnikov addition, but there is the possibility of carbocation rearrangement. If we instead carried out oxymercuration-demercuration, here we get Markovnikov addition without the risk of carbocation rearrangement. And finally, if we used hydroboration-oxidation, we would get non-Markovnikov addition of H and OH. So from the same starting material, we can get different products, and we can control which target we're going to obtain by selecting the correct conditions. Now for our third example, if we carry out acid-catalyzed hydration, we are going to get Markovnikov addition, giving us this product. If we do oxymercuration-demercuration, we are going to get the same product. And if we carry out hydroboration-oxidation, we are going to get this product plus its enantiomer. Non-Markovnikov, syn addition. Now, you can look at this as complex because there are so many different things that we can do, or you can look at this as being powerful because we can select what reaction we want to do to be able to obtain a particular target.